Hi everyone! Today we're going to learn how to write and balance nuclear decay equations. Now, it turns out that the process or the strategy for how you will solve these problems is essentially the same. So it doesn't matter which isotope is involved or which decay process is happening. The steps that you'll follow, the strategy that you'll use will be consistent across these different types of problems. Now, there are a few things that you need to know in advance as you're coming in to solve these problems. The first is you need to know which primary radiation particle is emitted from each of these processes, because that particle is going to become one of your product species, and it will actually set the stage for how everything else balances, how all the other numbers work out. The second thing you need to know is, what does AZX mean? What does that notation mean? Because you're going to be using it for both isotopes, which you are probably familiar with, and particles, which might be a little bit new. And then the final thing that you need to remember is that when you're trying to balance these numbers, what you're looking at is that the sum of the A values on the reactant side are equal to the sum of the A's on the product side, and the sum of the Z's equals the sum of the Z's. So let's take a look at what does it mean to have this AZX notation. So whether we're talking about an isotope, a nuclide from the periodic table, or we're talking about a radiation particle, the symbol is X. So you either get that from the periodic table if it's an element, or you know what it is if it's a radiation particle. The top number is always the mass number. So it's either the mass of the nuclide, the mass of the nucleus, or it's the mass of the radiation particle. The bottom number, Z, we know that as atomic number, but it is also equal to the nuclear charge. Because remember, we're talking about nuclei here. We're not talking about the whole atom. It is only the nucleus that is involved in these nuclear decay processes. So Z, while it is the atomic number, it is also equal to the charge. And that translates over to when we're looking at the particles. So the top number is the mass, and the bottom number is the charge. I just want you to be very careful that when you're dealing with the isotope part, when you're dealing with the nucleus part, that the Z is not ionic charge, as we might have learned earlier. Z is atomic number, it's nuclear charge, and when we look at the particle, radiation particle, it is the charge on the particle. I think we're ready to go ahead and start with the first problem. So the first problem is alpha decay of mercury 179. So one other thing, just as a reminder, if it's not already in the AZX notation and it's written as the name, the number is the mass number. So that way we know how to translate that into that AZX notation. So the first thing we're going to do is we're going to write the full AZX notation for mercury 179. We know that mercury has the symbol Hg, and we just established that the 179 is the mass number. So that's the number that goes on the top. We look at the periodic table and we find the atomic number for mercury, and we see that it is 80. So we write that number on the bottom. There's no other reactant here in alpha decay, so we'll write our arrow. And we're going to write the symbol for the radiation particle off to the side, so that way we can write the isotope first. So I'm just going to write a plus sign over here, and then I'm going to write the symbol for the alpha particle. So an alpha particle is simply a helium-4 nucleus. So we write the 4 at the top. Helium has an atomic number of 2, and that's what our alpha particle looks like. And for alpha decay, The only other product that we have is whatever that product isotope happens to be. Most of the time, you can look at the numbers here and do the math in your head. The math is pretty simple. I will tell you, though, that students often make a mistake. They'll add the number instead of subtract the number, and then it throws the whole thing off. So I'm going to show you just how the math works out, and you can write it out this way when you solve the problems or not, but you want to make sure that you are going back and checking that the A's equal the A's and the Z's equal the Z's, no matter which way you go about figuring out what the isotope is. So I'm just going to set it up algebraically. I know that the sum of the A's on the reactant side, I only have one, is 179. And that has to equal whatever I have for my isotope, the value of A, plus the value of A that I have in the alpha particle. So when I rearrange this math, I get 179 minus 4 equals X, which is 175. So the A value of my isotope, the mass of my isotope, is 175. And I'm going to do the same thing to figure out what is the Z. So I have 80 equals whatever Z value for the isotope plus 2. So I have 80 minus 2 equals 78. So I'm going to write that one down. So I'm just stacking the A and the Z. But I still don't know what the symbol is, and that's where the periodic table comes in. So I know that the value of Z for this isotope is 78. I look that up on the periodic table, and I find that 78 is the atomic number for platinum. And I write the symbol for platinum. Now you should always go back and check that the sum of the A's equals the sum of the A's, and the Z's equal the Z's, and 179 equals 179, 80 equals 80, and so this is the balanced equation for the nuclear decay, for the alpha decay of mercury 179. Our next example is for the beta decay of gallium 72. So I'm going to follow the same process that I did for the alpha decay problem. The first thing I'm going to do is write the symbol for my element. Gallium is Ga. I know that the mass is 72. And then I look up the atomic number, and the atomic number is 31. Just like the alpha decay problem, I'm going to write the arrow, and then off to the side, I'm going to give myself some room for the isotope, and then off to the side, I'm going to write the symbol for the beta particle. The beta particle is a high-speed electron, so it has a mass of 0 and a charge of -1. Don't forget the negative sign. And then we're just going to write that symbol as beta. So before we write the isotope, there's one more radiation particle that is emitted in beta decay, and that is an antineutrino. So the antineutrino has a mass of 0, a charge of 0, and a symbol that is nu with a bar over the top. So to figure out what our isotope is, we're going to use the same process that we used for alpha decay. So we have 72 on the reactant side equals X plus 0 plus 0. And when we figure this out, we have 72 equals X. So the value of A, the mass, doesn't change in beta decay. So that's pretty easy to spot. You actually, I don't think, need to go through the math like I did, but I just want you to know that you always have that as a backup. You can always figure it out like this if you need to. So we're going to take a look now at the Z. So we have 31 on the reactant side equals X plus -1 plus 0. When we do this math, we end up with 31 equals x minus 1, or x equals 31 plus 1 equals 32. So the atomic number for this isotope is 32. And then when we look that up on the periodic table, we find that that is for the element germanium. So we write the symbol as Ge. Now we're going to check that our A's match the A's and the Z's match the Z's. So we have 72 equals 72. That's fine. And then for the Z's, we have 31 equals 32 minus 1, which is 31. And this process is balanced. So I hope you're seeing already, even with those first two examples, as I've mentioned several times, that the strategy is the same. There's really not much that you need to memorize here. You need to know the radiation particles, but the rest of it is strategy, process, and those steps are going to be the same. So in this third example, we don't even need to figure out what the symbol is. It's already there for us. We're just going to write it down. So we have argon, 33. So we know that the mass is 33. We look up argon on the periodic table. It has an atomic number of 18. And that's our initial isotope. The process is positron emission, which looks a whole lot like beta emission. You just want to make sure that you're not confusing the particles. We're going to write the arrow, and then off the side, we'll write our positron. A positron is the antimatter for a beta particle, so it looks really similar. It has a mass of 0, but the opposite charge. So the charge is a +1. The symbol is the same. The only difference is the charge. We also have the other radiation particle, but this time it's the neutrino rather than the antineutrino. So the neutrino has still 0, 0, and the symbol nu, it just doesn't have the bar over the top. So the bar over the top is what distinguishes the neutrino from the antineutrino. Now we're going to do our math to figure out what our values are for the product isotope. So we have 33 equals x plus 0 plus 0, and that is 33. So beta emission and positron emission, the mass number doesn't change. For the Z, for the charge, we have 18 equals x plus 1 plus 0. And when we solve this, we have 18 equals x plus 1, 18 minus 1 equals x, and so that value is 17. So we write the 17 there. Look on the periodic table and we see that 17 is the atomic number for chlorine. When we check the balancing, 33 equals 33, and then for the Z's, 18 equals 17 plus 1, and this reaction is balanced. Our final reaction is electron capture. Our original nucleus, original isotope is cerium-139. So the 139 is the mass. We look up cerium on the periodic table and we see that it is atomic number 58. So that's the number that goes at the bottom. Now electron capture is the one reaction that we are studying that has an additional reactant. It's the electron. So the electron is captured by the nucleus, which means it is a reactant. But we're going to write this as a regular electron, not as a beta particle, because it really is a regular electron. It gets captured from the 1s or 2s subshell. So we're going to use the symbol E, and it has a mass of 0, an electron does, and a charge of -1. So while a beta particle is a high-speed electron, a beta particle is different in that it is created and generated in the nucleus and emitted or ejected out of the atom, but an electron is actually a regular electron like we know electrons. We write the arrow, leave a space for the product isotope, and write the primary radiation particle, which in this case is an X-ray. So the X-ray is produced as electrons shift around because that first electron was captured, and that is the high energy radiation that is emitted. This process also has a neutrino that is emitted. So we're going to write that one down. And now we're going to work on the math to figure out our product isotope. So we have 139 plus 0. We have to include what is going on with the electron now, because it's a reactant, equals X plus 0 plus 0. The X-ray has no mass and no charge, but it is not the convention to write those numbers there, and so we won't. But I'm just showing you here so you see that there are numbers attached to it. So what we end up with is 139 equals X. So the mass number doesn't change. For the atomic number, for Z, we have 58 minus 1 on the reactant side equals X plus 0 plus 0. 57 equals X. So our Z is 57, and then when we look that up on the periodic table, we see that that corresponds to lanthanum, La. When we check our math, we have 139 equals 139, and 58 minus 1, 57 equals 57, and this reaction is balanced.